All right, good evening. Do you have any question on anything before we start? No? So we'd like to start with Notes 3. So a few words about Notes 3. If you just don't work on Jupyter notebook sheets, but also have a look at the sample program sometimes, then you will have noticed in the sample program something interesting there in green. So that's why I want to put the focus on. And also the use of stars, calling functions like here, and defining functions sometimes. Explaining in Jupyter. So let me first start with this green part. Okay, so let me explain that independently of this particular problem. So if from the idle prompt or from the Python prompt I call the dir function, I get a list, which is the list of all attributes in the current module, right? So we have seen modules a few times. For instance, we have imported some functions from the random module, right? From import random, dir random gives us the list of all random functions available in this module, right? We have, from this module, imported some specific methods, for instance, seed, right? Today we'll work a bit with the math module. Math contains pi. What's wrong? I imported math, so to access anything in math, I need to type math dot. Okay, math.pi. That's the number pi, which is of type float. It's a floating point number, right? I can also work with the power function, math.power, which is not a floating point, of course, but a function. Okay, so a module is essentially a bunch of Python code where we find the definitions of constants, like pi, definitions of functions, like power, and any code we can execute, right? And we're actually always working in a particular module, right? So even at the top level, even there, at the idle prompt, the Python prompt there, I'm actually working within a particular module. And any module has a name. So dir lists all the attributes, everything defined now in this module. If I decide to define a new function f, not the most interesting function, but you see that now dir has changed and lists f as a new member of this module, right? So a particularly special attribute of this module is name. So let's see what name is. Is that good? No, I don't want to print the string name, right? Otherwise, I'm just going to get this sequence of characters. I want to print the attribute whose name is, between single quotes, name. That's what I want to print. And I find the string, right? So main is a string. Name is a string, right? Whose value is underscore underscore main underscore underscore, right? So that's the name of the module in which we're working, right? So now let's create a new file. Let's print name. And let's define a function, double, that's just going to return x times 2. Right? So if I save this file somewhere, let's say in desktop, sorry, a bit awkward. A great program, why not? Now, if I run this file, execute this file, I execute the print command, right, within the current module. So that's why I get main. I have also defined a function double, and now, of course, I can, knowing this function, double being now part of, right, double being now part of the current module, I can use double to compute the double of 3, 6. Okay? So I'm still working in this special module whose name is main. Now, if I try to import this module, right, because this code has been written in a file, and a file is nothing but a module, right? So by defining a great program with its contents, I actually define a new module. So import, what is it called? A great program. Now we get a different output, right? So the print statement now doesn't give us main, but something else, which happens to be the name of the file where this code was saved, right? So when you import a module, now the name of the module is the name of the file that contains this code. Make sense? So why is that of interest? Now let's see. I could see what's double of 0. I could see what's double of 1. I could see what's double of 2. See what's double of 34. And testing the double function here is actually a good way to explain to the user how this function is meant to work, right? So I could write comments over many lines, so between triple quotes. But essentially, it's just sample run of this double function, and with a bit of extra text, right? For instance, returns double of input, right? So a bit of explanations on how this function works, and then to convey the message even better, give examples of use of this function, right? So that's good. What would be even better would actually be to test that indeed this function is working as expected, right? And an even better idea would be to, before we even start to implement the function, well, of course it was straightforward, but to start writing essentially tests of this kind, right, to know exactly what we expect, and so that we can develop code and check how we're meeting these expectations. So for that, I have a particular technique, which is to import the doc-test module, and this module contains a particular function, test mode, that actually can execute these kind of lines, right, which represent Python code as if it was run from the Python prompt, and we report problems in case there is a particular problem. Nothing happens. I guess my function is correct, so that's not too surprising. Nothing happens either. Why is that? So actually, these commands should not be put outside the function. I can put it outside, but then it's just commands. But they should be put just after the def statement. And now if I run, it complains that this command should be indented. Right, so are we there? Good, now you see what's going on, right? So I wrote this specific, I wrote this command right after the def for the function definition. And the effect of this is to look for, within this command, any statement, right? So anything of the form triple greater than, as if I was working from the Python prompt or from the idle prompt, right? And to execute this code. And in case the code is correct, no output. But in case the code is incorrect, of course, assuming that our expected outputs are right, then it's going to report on every test that fails, right? So all tests fail here, right? Make sense? Now that's all good, but in case I'm importing, let me do it from there. In case I'm importing a great program, so why can't I output a great program from here? Why did this import statement fail? It doesn't find it. So why is that? So my great program is defined in desktop, right? So I'm working desktop here. How can I know? Well, I can import OS, DOS. Gives me a huge set of methods, one of which is get CWD, which means get working directory, right? So os.get current working directory tells me that that's where I am, right? So in case I want to import a great program, I would have to change directory. That's one way. So OS has a particular method. I want to change directory, change. So chdir should do the work. Change directory to desktop. now okay, on desktop, and now I can import a great program. Fine. Double of 3. What do I have to do? Always the same thing, a great program dot double, right? I've imported the module. So I can now access the method. Now, normally, I should also, when I import a great program, get the output of test mode. So why don't I get this output? Because I imported the module. So I guess I will test any test for the module, right? I could have comments outside double for the whole module. But I didn't import the function. I imported the module from which I can access the function, right? I access the function from the imported module, right? Now, if from this module I import the function, again, top test doesn't work. Okay, so I don't know why, because normally you would expect this to run as well, because the standard way to run this code only when you work at the top level, so only when you work with this module, where you define the function and where it's interesting in this module to test the function, okay, and to avoid running it when you use the module by importing it or importing functions, is to write this code, is to say if the name of my current module is main, then I want to test the code. But in case it's not main, it means I'm importing this module, and then I'm assuming that everything defined there works. I'm not interested in testing it. All right? So you see, running this code at the top level makes doc.test module work and output a problem in case there is one, not in case there is none. And here the name of the module is main, right? So that's why this test succeeds, hence this code runs. But in case you are instead importing the module, or importing a function within the module, right, then name will not be main, but will be a great program. And so this code is guaranteed not to run. Okay, so why didn't run this time? Not too sure. It does run sometimes. I have to investigate, because it always works like this. And it's not clear to me why, without this if statement, I still got no output of test mode when running this code. But it doesn't matter, right? What is important to understand is the use of special commands when you define functions that describe what the function is supposed to do, and then that test the function, and this code there will be run every time you run this program, you execute this file at the top level. Yes? Or just to show that the output was different depending on whether I execute this program by running it, in which case the output is main, or if I input it from if I import it I know I get it, yes. I know why. Because when we import, that's another thing, yeah, I'd forgotten. The import statement is only executed the first time you import the module. So if you make a modification to your program, then you need to re-import it, right? So there's another module that lets you re-import the module. That's what was happening. So let's comment this out. Making things incorrect. And now import a great program, except that it should be in the right directory. So let's just go in the right place. Import a great program. Try again from a great program. Import double. Still not. That was not the explanation. Even though what I said is right, that when you import something, if you modify the code, import has no effect, and you need to re-import the program using a particular function in a particular module. Anyway, you're not going to work this way right from the command line. You're going to work from Spider or PyCharm or any serious IDE that, of course, does all that automatically, right? So here we do things the hard way. And yes, so I need to understand at least why this is not executed when I import it, right? Because anyway, to answer the question, right, you see the output of print, it is a great program, right? So the name of the module is the name of the file that contains this code. But if I run this code at the top level, then the output of this is not a great program, but main, right? So it depends on the module where you are working. No, it needs to be saved, right? It's saved as a file with this name. Okay. See, it's saved as this name. Well, I don't have to keep it open, right? I can quit Python. I can quit idle. Let me also quit terminal. And I suspect it's because it's cached, right? So you see this directory which is created. Okay, so when we import something, somehow it saved as bytecode, so some code which is between Python code and machine code, right? So something intermediate. It saves it so that it can reuse it later. So my guess is maybe that if we delete that, let's try again. Python import a great program, still not. So because I updated to 3.8.2, so maybe things have changed since then. Because now I'm running out of ideas. Yeah, I commented out, right? Which means Oh, yeah, stupid me. Yeah. It's not what I wanted to. Don't want to print this out. Okay, so now this is supposed to run whatever the name of the module, right? Correct? This is supposed to run in any case. Let me delete this. Let me go to desktop, Python. week3. Incorrect. Delete this. Wait program import travel. I don't know, because I did everything possible there. All right, so so that makes this useless, even though up to now it has always been useful. So I need to investigate to understand better what's going on here, right? Because now this statement is useless. We don't execute it when we import the module. So maybe, yeah, I don't know, I need to investigate. Anyway, what's really important to understand is the use of these two lines, right? Import this module, run this function, which execute all the code between triple quotes that comments a particular function. That's very useful to check that your function works as expected as you develop code, right? Any question on this? Right, so it's a good practice. Now, if you work with any IDE, right, doesn't have to be with IDLE or anything. It's a good practice to, for every function you write, to start by writing comments of this form, right, to test your function as soon as you start developing it. So that's all I could explain, not talking about the problem of Notes 3. So let's say a few words about Notes 3, the problem. So what's the difference between a rational number and an irrational number like pi, e, square root of 2, and so on, right? What is the difference between these numbers, irrational, and fractions, like 70 divided by 362? When you write them in base 10 as 3 dot, and then for pi, what is it? 1. We've imported pi before, so if I want to have a bit more than just 2, right. So what's the difference between fractions and these kind of numbers? How do we know if a number is irrational? When we write it in this form. When you divide, what happens is that at some point you have some pattern that repeats, right? 1/3 of years, that's 3 repeats, right? If you take any fraction, so it's not going to be always immediate to see. So we have 2.7, and then again the simple pattern 3 that repeats. So, of course, the pattern can appear anywhere and can be very long, right? So you might have to wait for 1 billion digits before you see the beginning of the pattern that might be of any length, all right? So I'm not very lucky now to show you a good pattern. We don't see any good pattern anywhere. Well, it's how I like this one. The notes have good patterns. Last attempt. This is either it's trivial or it's okay. I can't get a nice pattern. 615. 23 divided. Ah, here you say. Oh, yeah, you're right. Yes, I was so desperate to look for a good pattern that I didn't even see it. So 615. 3, 8.
So the beginning 3, 8, 4, 6, 1, 5, 3, 8, 4, 6, 1, 5.
Okay, you see it? Good. So essentially, a fraction is always of the form, right? Some digits. Of course, if the number is bigger than 1, 2, 1, 7, 6, blah, blah, decimal point, then you will have some digits, sigma, and then a bunch of digits, tau, that will repeat forever, right? With a number like pi, you can look as long as you can. You will never, ever see a pattern that repeats, okay? By the way, is this representation unique? Well, it's not, because 1.0, that's also equal to 0.999 forever, right? The same number. So unless your number after some point stops, is nothing but zeros, in which case, okay, so if you have any number 0.416, okay, that's equal to 0.415, and then nothing but 9s, right? So that's a special case. If you have a finite number of decimal values, then you have another representation, which is last digit minus 1, followed by nothing but 9s, okay? Otherwise, it's unique. So now we can work on a particular problem. Given sigma, given tau, right? So if I give you sigma, let's say, which is 3, 3, 4, I give you tau, which is 76. Okay, give me the number between 0 and 1, which is of the form 0 dot sigma and tau forever, right? So here's 0 dot 3, 3, 4, and then 7, 6, 7, 6, 7, 6 forever, right? So give me the numbers P and Q, such that if you divide P by Q, you get this number, right? We know if it repeats, it's a fraction, so give me the fraction, and in simplified form. So how do we solve this? Well, it's not really hard, right? You just have to do the maths. So if our number P divided by Q is of this form, it means okay, it is equal to 0.334, which is sigma to the power, it's equal to 334 times 10 to the power minus 3, right? Plus, so that's for the contribution of sigma, this, right? Plus, we have the first tau, so 76 times 10 to the power we want to account for this. So minus 5, right? Plus, we want to account for this. So 17 times 10 to the power minus 7, and so on, right? So more generally, it's sigma times 10 to the power minus the length of sigma, right? Plus tau times 10 to the power minus sigma minus tau plus 10 to the power minus sigma minus 2 length of tau, and so on, right? So adding minus the length of tau forever. So it's just a geometric series, and you can just compute it, right? So if we do the maths, we just get an expression which I don't spend time to compute here, it's not worth it. We get this formula, right? Sigma times, so you see, since we use the lengths of these numbers, right? So it's actually convenient to pass an argument to the function, not the numbers, 334, 76, but the strings, 334, 76, right? Because we use the length. And then we get this particular formula involving both the value and the length of the string that represents this value. All right, so it's convenient to have sigma and tau as strings, and then we can use the length of these strings when we need, and when we need the value, so sigma times 10 to the power minus the length of sigma, right? So length of sigma, that's len of sigma, and sigma times, that will be, of course, int of sigma. So then we convert the string into an int, right, to perform the computation. Make sense? So let me just, yeah.
So we don't know how many times
Forever, right? So, well, it's a geometric series, right? So I'm just using the fact that x plus x2 plus x3 forever, right? That's 1 minus x, right? That's what we know. Well, that's the limit of a geometric series, right? So that's what I use here to compute the limit. Okay, so let me open Jupyter Notebook sheet. And let's just copy and paste this code. Where is it? Let me remove all these commands so that we can see better. Right, so compute fraction. So we say tau is, what was my example? It doesn't matter. 33476. So 33476. So that means if I divide this by that, I should get indeed 0.334 and then 76 that repeats forever. Right? Modulo the maths which are skipped, I let you check it by yourself, right? So this function, compute fraction, is supposed to get two strings because it needs the length of the strings. Let's define another function. Def give me sigma and tau input, give me sigma, that will be sigma, give me tau, give me tau, and let's return sigma and tau. So remember, we're not returning two values, right? We are returning a pair, right? A tuple with two elements. What's wrong? Have a function taking no argument, but needs parentheses. So now I can call this function, give me sigma 346, give me tau 74, 73. It returns these two strings. Good. So what I would like, of course, is to pass these two strings, right, to my compute fraction, right? So what I would like to do is to pass sigma and tau to compute fraction. Give me sigma 54, give me tau 76. Oops, something is wrong. What's wrong? It explains to you why. What's the issue? Not really, right? Look at the message. What does give me sigma and tau return? It returns one element, which is a tuple, right? A pair. What does compute fraction expect? Two elements, right? If you think about it, how does print work, right? When you define a function like compute fraction, well, you define it with a given number of elements as arguments. You have to decide how many elements, right? 1, 2, 3. That's it, right? In some languages, you can have many definitions of the same function, accepting a variety of arguments, right? Python doesn't let you do that. Define one function. It has to work whatever arguments you provide, all right? Print looks like a magic function because you can call print with no argument, one argument, two arguments, three arguments, right? It's a magic function. So how can print work and accept an arbitrary number of arguments? Well, of course, there's a trick, right? So Python lets you actually group together a number of arguments into one tuple, right? You see that later. But now, what we can also do is here let the output of give me sigma and tau, which is a pair, be dispatched into two individual arguments. So if you like, magically remove the surrounding parentheses, right? So now if I put here a star, it means this pair output by give me sigma and tau is going to be changed to first element, second element of the pair. Okay. And now I got my fraction, right? Which hopefully 34778 as requested. Right, so very useful syntax, right? So you see you can, this way, pipe the output of one function and make it the input of the next function. Yes, so it has to match, right? Since the function expects two output, you have to unpack a pair, right? If I try to unpack a triple, it would complain that I pass 3 arguments when I expect only 2. That's right. The star applied to any tuple. So okay, let's continue. What is bad about this fraction? Well, it's great in the sense that it solves the problem. It reads as we want, but it's not optimal because do you like this fraction? It could be simplified, right? It's 2 even numbers at least. So we like to simplify the fraction. How do we simplify the fraction? We have to divide by the GCD of both numbers, right? The greatest common divisor of both numbers. Of course, the greatest number that divides both by definition, so you can divide both by this to simplify your fraction, and you won't be able to simplify it any further. Right, so I could now define the function, simplify fraction, and it's nice to say, well, I have function p divided by q. I want to compute the GCD, so we'll see how to do that in a second, but if you want to be lazy, we can just, from math, import GCD and compute GCD of P and Q, which will be some number n, and we just return P divided by n, Q divided by n, this way. Not exactly. If we do this, it's going to be floating point division, right? I want integer division, because of course I get an integer as a result. So for that, I have to use. All right, so if I call my function simplified function on these two things, I get these two numbers, and if I divide these two numbers, hopefully I get the same result. Yes, I do. And the fraction is simplified. Right? So same story, you see, I could now have a longer pipe when I say, give me sigma and tau, compute the fraction, and then simplify it. It's even nicer if we just write simplify instead of simplify fraction. It will read even better when we pipe it. A complete fraction and simplify it. One more. 78. Of course, what's wrong? Same thing, right? Compute fraction returns a pair, right? No, where's compute fraction? There, right? It returns a tuple, a pair. So I also have to apply the star there, right? And I've got my simplified fraction. Okay, and I could add one more layer, say print out result, and same thing, right? It would be nice to define this function as taking 2 arguments, and again the star would make sense. So very useful Python syntax, right? That star applied to the output of a function. And as I mentioned at the beginning, you can also use star in a function definition. Let's see that. F of nothing, we return I put together all arguments. So what do I get? An empty tuple. Then I call f of 1. What do I get? I put together all arguments. So I get the tuple 1. So I get, between parentheses, 1, comma, right? Without the comma, it would just be the number 1 surrounded by parentheses. And on it goes, right? So that's exactly how print works. You see, now my function f now accepts an arbitrary number of arguments, puts them together into 1. Make sense? So if I do f of, what will be the output? As opposed to what will be the output? Understand? The second one, f returns the empty tuple, right? With a star, we dispatch the contents. So essentially we get rid of the surrounding parentheses, right? So now we don't have an empty tuple, we have nothing. Pass an argument to the second call to f. So f gets nothing and puts together nothing, right? Here on the other hand, f returns an empty tuple, which is not nothing, right? Which is an element which is the empty tuple. And we put together all the elements we get, which is the empty tuple, right? So we put together the empty tuple. Make sense? Right, so play with that. We have a few examples in the notes. F of 1, 2. What will that be? I guess it will be 1, 2, package that by this f into a new tuple with only one element, because this returns one element, put together by this f. Right? On the other hand, do this. I'll let you play with that, right? You have plenty of right, so there, right? X times 2 is a great example, right, where you duplicate a particular list, and we see what happens by, putting the star at various places. Right? So go through this example, and then you will understand, master fully the use of star, both in function definitions and function calls. Right? So, but it's a very important technique to master. You use it a lot. Okay. So maybe to finish on that, just comment on the GCD function. If we were not lazy, if we had to compute the GCD ourselves, how do we compute the GCD? If you have two numbers, let me not guess because I'm not good at guessing, as you have noticed. So take a reasonable example. No, that's not a good example. Of course, it's trivial. So how do I compute the GCD of A and B? Well, I just have to divide A by B, right? Look at the remainder, and the GCD of A and B is the same as the GCD of B and what remains of the division of A by B, right? So if I divide 1, 2, 3, 3 by 999, I get this number. What I want is what remains of the division. So that's the integral part, and that's what remains. Okay? That tells me the GCD of these two numbers is the GCD of 999, 990, and 243. How do I compute the GCD of these two numbers? So same thing. I divide the largest by the smallest, and I take the remainder. That tells me GCD of these two numbers is the GCD of 243 and 18. And for that, I divide this by 18, first one by the second one. I get a GCD of 9. So it should be the GCD of 18 and 9. And now, of course, I should be done because 9 is 2. 18 is 9 times 2. So if I divide 18 by 9, of course, I get a remainder of 0. That tells me the GCD is 9, right? Okay, no mistake. Fine. So how do we implement this? My GCD of A and B. Right, so eventually we are going to have two numbers. The second of which will be 0, right? And the first one will be the result. So in other words, for as long as the second number is not 0, I have more work to do, right? The GCD of A and B will be the same as the GCD of the second one, B, with the rest of the division of A by B. Isn't it? And that will become my new A and my new B. And eventually, I return, when B equals to 0, I return A. So my GCD of, of 2, 4, 3, and 18. So, what do I have to check? Well, that's okay, right? For as long as B is not equal to 0, right? Because a number is equal to 0, it's converted to Boolean false. Yeah, that's obviously, I try to do something recursively, right? That's what I want. Simpler than that. Okay, so it's worth understanding what's going on there, right? If you want to, so what did we have? We had 2, 4, 3, 18. A equals to 243, B equal to 18. We compute 8% B, which was equal to 9. Right? So we wanted to say, now our new A becomes the former B, and our new B becomes A% B, right? That's what we wanted to do, right? So in most languages, what would you have to do? You could not directly say, let's B be equal to A% B, right? Because that would make the new value of B be what you want, but the new value of A should be the old value of B, which you have lost. And if you make A equal to B first, then you haven't lost the old value of B, but then you have lost the old value of A, right? So you are stuck. So what do you have to do? You have to save the old value of A, right? Let C be equal to A, so that's the old A is remembered. Now you can overwrite this old A with B, it becomes a new A, right? And now you can make B equal to C% B, right? So you need an extra variable, right, to remember at least one of A and B before you perform the computation, right? So you see how nice Python is, right? It doesn't need this extra variable, right? So how does it work? Well, you always have to think of, when you have an equality sign, an assignment, that I first evaluate what's on the right-hand side, and then I assign what's on the right to the left, right? So you have A, which has some value. You have B, which has another value, right? So you compute A% B. Okay, so now you've got a pair, right? A tuple with two elements, your B and A% B. So your B, which is the old B, and A% B, which is the new B, right? And the old B has to become the new A, right? So you see, it's clear when you look on the right-hand side, you evaluate this pair, you evaluate this tuple, evaluation of B, well, that's wherever it is, evaluation of A% B, you compute it. So now you have two values, a pair, right? And then you assign this pair to the left-hand side by making the first element of the pair on the left-hand side A equal to the first element of the pair on the right-hand side, what B evaluates to, and same thing for B, right? You make the second element of the pair on the left-hand side have as value the second element of the pair on the right-hand side, right? So it's clear if you read things properly, evaluate what's on the right-hand side, and then assign element by element. And of course, as we know, it works because we have tupled with the same number of elements on both sides, right? You can't assign a triple to a pair or a pair to a triple, right? You can only assign a pair to a pair, a triple to a triple, because it works element by element. Right?
What's the meaning of the percent?
Percent means reminder, right? So I think I had that somewhere. I lost it. Okay, so 243 divided by 18 gives me some number, and 243% 18 gives me another number. And that means that if I multiply the result of this 13 by 18 and add the remainder, 9, then I get the first number, right? So this is the number of times we can fit this second argument to the first one, right? So that's integral part of the division, and that's what remains. So what couldn't fit as a whole. And I said last Thursday that you can have both together using div or mod div. Mod div mod. Yeah, division modulus. It's more logical. Right? So it gives you // and percent together. Okay? Is it fine? Should we take a break? Almost late for a break, right? You want to break or not? Yes? Okay, so a short break. No, that's right. Yeah, it looks like you have a good idea. It is a good idea. It's something.
There's two functions. There's the amount, even that one takes at least a minute. You just say, please come in. Yeah, at least. How do you finish the other one? Unless you find a pattern.
Then you find
There's a pattern.
it's too hard. Too hard. You need to find the patterns and you need to decide what happens. Then you can find the shortcut.
Yeah. Look, don't tell me 6 months. First one, 10 million.
Maybe
Maybe first one, definitely. First one, like 10 million elements from like unless you have a shortcut, you don't count the profit.
yeah, you know the like you said, then you know you just need to
Yeah, same with something like that. Unless you have it's rapid. It's simple.
Okay. Okay, so let's get back to work. And see techniques to find prime numbers. All right, so we look at notes number 4. And we'll learn about zip function. We'll learn about matplotlib, how to plot data. And we understand in depth, have good insights on what's efficient, what's not efficient when we work with lists, when we work with sets. So very interesting to have a deeper understanding of what's happening behind the scene and make sure that we write code which is efficient enough. But I don't think I will have time to go that far today, so I start explaining the problem, and we write as much code as we can, but we won't tell the whole story today. All right, so I want to generate all numbers, all prime numbers in a given range, right? So let's say all prime numbers from 2 up to, I don't know, 10 million. Right, so as we still know that when we work with lists, it's very efficient to access an element from its position, but it can be costly to find an element in a list, right? If you have 10 million elements and you want to find out if your list contains a particular element, you have no other choice but, unless your list is sorted, but if it's a random list, you have no other way but to look for this element in the list, starting from the first one. Is it the one I want? No. Next one. Is it the one I want? No. Until you eventually find it, or exhaust all elements of your list and conclude, no, my list doesn't contain this element. Right? So indices give us fast access. So that's the idea behind this sieve. Instead of storing numbers in a list, we are going to use a list of length maximum number, our upper bound, the largest prime number of interest, right? And say at this location in our list, we'll have some information about the number, whether it's prime or not. So 0, that will be ignored. It's fine to waste the cell. 1, that will be ignored as well. But 2, 3, 4, that's all locations of interest, right? And essentially, we want to have these cells contain true if the number is prime, and false in case it is not prime. And then once we have done this, we can use that in two ways, right? Either generate all numbers, all prime numbers in this range by just scanning the list and outputting all elements where we store the value true, or just ask if a number in this range is prime by just going to this location and see if at this location we find true. All right? So I guess we have two options. Either we assume that everything is true, right? So we put true everywhere to start with, and we kill numbers as we go, or we start with everything being false, and we make number true as we go, right? This one or the other. Well, it turns out it is going to be the first method, right? So we assume that everything is true, and then if we proceed properly, we're going to kill some numbers. You know, actually, this one is not true, this one is not prime, this one is not prime, so change some true to false. So how does it work more precisely? 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Let me go up to 23 maybe. Right, so this will be indices, remember, right? So index 0, we don't care. Index 1, we don't care. Index 2, that's where things really start. All right, so the first number greater than 1 we find, it is prime because it's not divisible by anything smaller except 1. So we know 2 is prime. And then we can eliminate all multiples of 2, right? So 2 times 2, 4, 6. So I should not do that, not to confuse you, right? So but instead of having true everywhere now, okay, so this is true, we're going to make this change from true to false, right? So all multiples of 2 can be killed, discovered not to be prime. Right? So that's what we got, that's what we did by processing the first element of interest in our list. Then we go to the next element, 3. We find that it stores the value true. We have the value true at this location, so it means 3 is not divisible by anything smaller, except itself and 1, of course. So it is prime, and now we can eliminate all multiples of 3, right? So 6, already killed. 9, 12, already killed. 15, 18, already killed. And 21. Okay? Then we go to 4, and we see that at location 4, we have the value false, which means the number is not prime, so we can ignore it. We go to the next number, 5. We find the value true we had originally, which hasn't been overwritten by false. That tells us 5 is prime, and we can now kill all multiples of 5. So 10, killed already, 15, 20. We don't kill anything more. Of course, if we had been up to 25, then it would be killed. 6 contains false, is not prime. 7, true hasn't been overwritten. We can eliminate now 14 and 21 for no benefit. 8, 9, 10, you get the idea, right? And 11, which kills 22, done already. 13, and all other numbers we find are found out to be all prime numbers we find. Okay, don't let us eliminate more numbers. That's fine. That's 23, right? Not 33. That's 23. Okay, got the general idea? Okay, it's not very good, but let's just start with that. So def prime up to, I have a number n. So what do I have to do? I have to define this list, sieve. I assume that everything is prime, right? And this list should have a length of I want all elements from 0 up to n, so it should have a length of n plus 1. Okay? And then I look at all elements, all locations of interest. The first interesting location is location number 1, location number 0, not interesting. 2 is the first location of interest, right? And last location of interest, of course, is n. So I go at that location. If I find out that at that location the value is false, it means the number has been found out not to be prime, thanks to the job done so far, right? I can just ignore it, right? I'm just going to kill all the multiples of prime numbers. So if not sieve of I, it means that the number, if you like, if sieve of I is equal to false, right? Is that is the same. I prefer to write it this way. I is not prime, so it's not interesting to eliminate more numbers. So just continue, which remember means go back and generate the next I, right? Otherwise, we want to eliminate all multiples of I. So how do we do this? J in range. The first one I'm going to eliminate will be the first multiple of I, except I itself, will be I times 2, right? And we want to eliminate I times 2, I times 3, I times 4, up to potentially any number that doesn't exceed n, right? So range, now let me say I want to start from this number, right, starting point, that's the limit. I don't want to reach that number, right? So as soon as I reach n, I stop. And if I write it this way, I'm going to look at I times 2, I times 2 plus 1, I times 2 plus 2, and so on. I'm going to look at all numbers, right, in the range from I times 2 up to n included. I don't want to look at all these numbers, right? The next one should be I times 3. Next one, I times 4. So I want to jump from a number to that number plus I, right? I want to add I every time. Right, so that's the whole most powerful use of range, right? So from this number included up to that number excluded in steps of with a number. So for all of that, I want to say all these numbers, they're all multiples of I. So at that location, I have to put false, right? Make sense? Maybe it's false already, but
How did you define range
okay, so let me see. So range 2, 18, 3, that gives me this, because it's an enumerator. But if I say, give me on demand all elements in this range and make a list out of that, you see, I start with 2, and then I keep adding 3. So 2 plus 3, 5, plus 3, 8, plus 3, 11, up to the largest number obtained this way in steps of 3, less than 18. Make sense? I have example. Tuple, range 10, 85. Right, so all multiples of 5, if you like, it's all multiple, all, not, well, here's because I start with 10, which is a multiple of 5. But, okay, all numbers in steps of 5, starting from 10, stopping before 80. Right? It's fine? So, at location j, I put false. See, j, being a multiple of I, is not prime. Maybe at that location I have false already, right? Maybe j was killed before. I don't need to check if at that location I have true to change true to false. It's not worth it, right? So it's better not to check and just either overwrite false by false, or just overwrite true, which is not useful, or overwrite true by false, which of course is useful. Okay? So let's test this function. And eventually, I can return R. So what do I want to return? I want to return all locations where my list stores true, right? So I want to return I for I in everything between 2 included and n included, so n plus 1 excluded, provided that, so if my list at that location is true, right? Make sense? Where do I return? What is the type of what is being returned? Is it a tuple? No, it is a generate expression, right? So something to which I can apply next, and I can say, give me all of that as a list. 2, 3, 5, 7, 11, 13, 17. Okay, it looks reasonably okay. Prime numbers up to 100. Is it fine? The last line.
Yeah. How does it know if it returns was a true or was a prime number?
Because I say give me I for any I in this range if my list at this location stores the value true. Right, which you can just say this because Steve of I evaluates to true or false depending on whether its value is true or false. Right? So remember, okay, I really insist on that because that's really important, right? If I do things this way, then I return the list, right, directly, but I prefer to return that. And then now I could say x, so primes equal to this. So primes is a generic expression. Then I can call, give me the next prime. Give me the next primes. Give me the next primes again and again and again. Right, now these elements are generated on demand. Right? That's how you should always design your programs if you don't want actual list, but you just want things to be generated if needed, when needed. Any question on that? So it's not great. You can improve things in many ways. Right? When we did it by hand, we saw that we overwrote false by false many times. Right? So can we save a bit of time, not compute things again? So first, if I look at, so I've reached number 11, right? So it means I'll have eliminated multiples of 2, 3, 5, and 7, right? Now I'm eliminating multiples of 11. What is the first one that I eliminate here? I start with 11 stair, right? 11 times 2. Is it useful? 11 times 2 is a multiple of 2, right? So gone already. Next one will be 11 times 2 plus 11. 11 times 3. Useful? No, it's a multiple of 3. I already got rid of all multiples of 3. Next one, 11 times 3 plus 11, etc., etc. All that is useless, right? When does it start becoming useful? What is the first multiple of 11, which I know I haven't eliminated before? Yeah, exactly, right? 11 square, right? 11 times something at least equals 11. Everything else is less, so has been eliminated. So I can indeed improve things by looking at I to the power 2. Right? Much better. Then, how far do I go? What is the last number I look at? It's there, right? What is the last number I look at? When I look at all numbers up to and including 100. I look at 100, right, as the last number. And before that, I look at 99. And before that, I look at 98. Is it worth it? Well, if a number is not prime, right, you have your upper bound n. If n is not prime, it means it's of the form P1 times P2 times Pk, right? Where all these guys are prime. And you order them from smallest to largest, right? So it could be 2 times 2 times 11 times 19 times 19, right? So if you order all the prime products from smaller to largest, right? So with P1 less than or equal to P2 to Pk, right? So your number n is this. So it means it's, because k is at least equal to 2, right? Because your number is not prime, so you have at least 2 prime factors. So at least equal to P1 times P2, right? And since P2 is at least equal to P1, that's at least equal to P1 square, right? Which means that P1 is at most equal to the square root of n. Right? So if a number is not prime, it has a factor which is at most equal to its square root. Okay? So I can improve things further by not going up to n, but going up to the square root of n included, right? Because of course, if I'm looking at the number 100, right, I want to eliminate 10 square, even though it's going to be eliminated by its multiple of 2. But if I look at 11 square, right, 121, I will find out it's not a prime number when I reach 11. 11 square is 121. I knock off 121. Right, so I need to go up to the square root of my number included. So square root of n plus 1. So of course, it's not going to make any difference there. Primes up to 1000. Except that square root function, as it says, is not defined. What do I need to do? I need to import it from where it is defined, which is math module. From math, let's import square root. And now, still complaining. What's the issue? Float object cannot be interpreted as integer. Yeah, square root, all right. If you have a look at, even if it's square root of the perfect square root of 4, it's 2, but it's 2.0, right? It is the floating point 2. And range accepts as arguments, starting point, end point, step, all that has to be integers. So I have to convert square root of n from the float to an integer. How? Int. Okay, so we have to be careful, right? So if I compute the square root of 121, I would expect that to be 11, right? But is that guaranteed? Floating point operations can actually be imprecise, right? So maybe I get 10.99998, in which case int of this will be 10. Is that good? No, because I won't test 11 square, and I will conclude that 121, if it's my upper bound, is prime, when it is not. All right, so maybe I don't want int, in case my evaluation of the square root is just a bit below the right number, but what is closest to this, and for that I can use the round function, right? So int of 9.9, int of 9.1, all give you 9.9, but round of 9.9 and round of 9.1 are different because they give you the closest integer, right? And you ask me for .5, that's the numbers closer to 0, right? So that would be 9 for 9.5 and minus 9 for minus 9.9. Right. And you can also use round with the second argument. So if you ask round this number with 3 digits, right, it gives you the closest number close to the approximation of this number to 3 digits. Right. So let's use round for this. And the notes tell you bigger story. Actually, when we work with perfect squares, it looks like square root is always correct, but we don't want to talk about it here. But look at the notes that tell you more about the whole story. Okay. So we could now, is it 5? What is it? 4? No. It's 5? Yeah. So I wrote that in a piece of code. Essentially what we wrote. So that's exactly what we did, right? This is this piece of code, exactly what we did. So how do I check how efficient my function is? So of course, from this import everything. And I could try to have it as a list. If sieve of I, then print I. No. What do I have to do? What does this function return? Return sieve. So I have to call my function first. And then yeah, I don't need to look at indices, right? Yeah, I do. Not good. I can't look at the elements of my list, right? Otherwise, I just get true and false. So I have to look at I in range of 2 up to this number plus 1. Well, look, it's taking too much time, right? Let's just output the list. I for I in sieve. If for I in range of 2 to 1000, if sieve of I, right? Okay, let's try with 100,000. pretty good. I should 1 million. It's cleaner this way, right? If we don't hard code this upper bound. $10 million. Oops. So it took a couple of seconds, right? So I guess 100 million is going to be a bit too much. Okay, let's give up. Maybe just a matter of less than a minute, but we are too impatient. So of course it's not very professional, right? So it would be nice to be able to time the efficiency of our code. So let me show you this, because we don't have much time, only 4 minutes left. So I show you the end that we can use. The time it function. Right? So we see we can, from a particular module, which is time it, right, import a particular function, which is time it as well, right? And how does this function work? It takes first the statement you want to measure, evaluate, and whose efficiency you want to measure. All right, so if we ignore the second argument, it's going to tell us, I don't know about sieve of primes up to. Right? So it would work with time it L equal to 1, 2, 3, L dot append 4, right? Because it knows about list, knows about append. But this is not a built-in function, right? It's a function that we have defined ourselves. It doesn't know it. So second argument, you see globals. You have on one hand a keyword argument with the word globals, and it's assigned the value of the function globals. That returns all the names which are defined in the current module. All right? So if in the current module we define this function, the globals function written in the dictionary, one of whose keys will be sieve of primes up to, and whose value will be the function definition. So that's what we need to evaluate something which is not made of built-in statements. And then how many times I want to execute this statement, because time it by default runs it, I don't know, 100 times, it depends. Right? So we say we just want to execute this function call, we just want to evaluate this statement only once. Right? And you see that 10 million, that gives us a bit more than a second and a half. And then there was a second sample program, which I will let you look at, where we just eliminate multiples of 2 from the beginning, right? So we just ignore the multiples of 2. I let you have a look if you are interested, and that allows us to cut the running time by a bit more than 1/2, right? But you can ignore that if that's fine, right? But, so time it, of course, is a function good to know and good to use, right? Then, of course, you can design code to time your functions in a more systematic way and get. But we'll talk more about it as well, right? So we'll see good use of time it on Wednesday when we understand better how lists and sets work and compare, right? So we're going to use it a lot. All right, I think I have to stop now, so see you on Wednesday.
I just want to ask for the previous question.